Hi, everyone. My name is Colleen Bertoni. Like Yossi said, I'm in the performance engineering group at ALCF. A lot of what I do is work with applications to help prepare them for Aurora. And yeah, like Yossi said, I'm sick and I didn't want to spread, infect everyone at the workshop today. So I'm presenting over Zoom. I'm very sorry not to be there in person. Luckily, it's not COVID. I did get that tested. So I'll be giving a quick introduction to OpenMP on Polaris today. This is just 10, 15 minutes, and then there's a longer 2.5-hour session with Yalo later in the afternoon. So let's get started. First, why would you want to use OpenMP? I think most people are familiar with OpenMP, but I will go through again really quickly. So OpenMP is an open standard for parallel programming. It's basically an API and environment variables that a lot of different vendors have implementations of. The specification is all open and it's at that website. The document is very large, and the main reason why it's so large is that it's very broad and expressive. So it can run on the CPU threads, GPUs, specific units like SIMD units. It also has support for both C, C++, and Fortran. The vendors behind the other new supercomputers at NERSC, Oak Ridge, and also here, so Perlmutter, Frontier, and Aurora, all provide OpenMP compilers and runtimes, in particular the OpenMP offload. So using OpenMP to run on GPUs as well is supported. It has a pretty wide support by Intel, HPE, AMD, GNU, and LLVM compilers. And so because it has wide support, OpenMP offload is nice because in the best case scenario, you write your code in OpenMP offload and you can run it across all the large DOE systems. So for Polaris in particular, so like Brian talked about, most of the compute power and memory bandwidth is on the GPUs. So for Polaris, like we really want to focus on running on the GPUs. And since the GPUs on Polaris are NVIDIA GPUs and CUDA is NVIDIA's programming model, why would you want to use OpenMP offload instead of CUDA? One reason was what I just mentioned, was the fact that it's portable. The other is really, it's very easy to get started. It's pretty much trivial to parallelize a loop if you already have that in your code, like for C, C++, or Fortran. And also OpenMP offload has some nice convenience functions or convenience directives. Like for instance, the reduction clause simplifies data reduction for you. So just going over the OpenMP compiler support for GPUs to make it very concrete. Right now, there's support for all the sort of the three main HPC GPUs, NVIDIA, Intel, and AMD. NVIDIA has pretty much the widest support of vendors which allow you to target it. Sort of shown here, LLVM, HPE, NVIDIA, IBM, and GNU. Intel at the moment only has Intel, but maybe that will change in the future. AMD to run with OpenMP offload on AMD GPUs. There are a couple of different vendors that support it, but overall, if you want to use OpenMP offload, you can do this on all the different GPUs, at least that are common in the HPC space. So just diving right in. So I think most people are familiar with CPU OpenMP offload. So let's say you, like for previous insight or running on a previous system at Argonne, you went through a bunch of work to parallelize your code with OpenMP for CPUs. So basically you found all the areas that were parallelizable. So like, for example, in this case, you had a for loop over num steps. You added pragma OMP parallel for, so that you would spawn threads, or parallel do for Fortran, so that you would spawn threads with parallel and distribute the iterations of this loop to the different threads. But like I said, a lot of the new systems are using GPUs now. So the nice thing with OpenMP is that you can still take advantage of the work you did to parallelize with OpenMP for CPU, at least as a starting point. for running on GPUs with OpenMP offload. So for example, for this case, you already went through and decided to parallelize with OpenMP for CPU. So as a first step, to move to running on GPUs, you could just take that and change the directives. So instead of pragma OMP parallel 4, pragma OMP target teams distribute parallel 4. So to some extent, the same thing. These directives, instead of just running on the CPU, will now launch it and run it on the GPU. Of course, these directive names are different. So what I'm going to do in the next couple of slides is, just a first step, explain what these different directives are from the CPU side and why they would be different than just why not have OpenMP parallel 4. So just to go through these basic OpenMP offload mechanisms, at a high level, there's sort of three things you want to do when taking CPU code and GPU code, which is just marking which code you want to offload and run on the device or the GPU, and then expressing parallelism, so saying which parts can run in parallel. And then a really important one is mapping data, so transferring data from the CPU to the GPU and back. So going through those clauses, just to make sure you understand it. So again, the program model in OpenMP is that there's a host, the CPU, and a device, the GPU, and we want to move data back and forth between the host and the device and execute code on the device. The device is here. These smaller boxes are on an NVIDIA GPU. It's composed of smaller scalable units called string multiprocessors. And this is important to understand because inside of the string multiprocessors, there are resources that are shared there, like shared local memory, which aren't shared running in between the two SMs. So having multiple threads running inside a SM can share some resources, but those wouldn't be shared between a thread running on one SM and a thread running on a different SM. So it's just important to know the sort of hierarchical structure, and that there's one NVIDIA GPU composed of SMs. So the target construct is the one that says to take any code that's inside of an offload region and run it on the GPU with a single thread. It also transfers data with implicit and explicit rules, but for now, just think about the directive as change from having a CPU thread running along. Once it hits the target, it switches to running on the GPU. And of course, the main thing is, although this will offload to the device, it still runs in serial. Serial is, of course, not what we want because we want to be able to take advantage of the GPU. So to get more threads, the first thing is to add the teams construct. This is what creates a league of teams. Each team only has one thread active, and that's trying to show that in the picture with the dark thread. But they're running concurrently. This is sort of a coarse-grained parallelism that just says league of teams, and each team will run on an SM. So in the tiny picture, there are 3 teams running on different SMs, each with only one thread in it. Then the parallel construct is what creates the threads in the teams. This is pretty identical to the CPU side, where the parallel construct was what created the threads team. And then this has all the threads which you can running on the different SMs. So sort of putting that together and looking at an example, we have target teams parallel to create the target teams parallel, which create the teams and run them on the GPU, and the distribute and for, which are distributing. So distribute is distributing the work in the outer loop to the teams, and the for, just like on the CPU, distributes the work between the threads in the parallel. So the last thing I wanted to mention was data mapping. This is important because it's usually much slower to access memory across the PCIe than directly to memory. So if you have to do a lot of data transfer from the CPU to the GPU, it's slow. And this can sometimes be tricky in OpenMP because they're implicit data mapping rules. So here we want to take the X array on the GPU, read it, multiply it by 2, and then ideally do something with it later. So this is using the map clause. Map is a directive which handles data transfer in an explicit manner. So map to from says, the to says map from the CPU to the GPU, and from says map from the GPU back to the CPU when you're done. So that's explicit data transfer. However, there's also implicit data transfer with the target, and usually it's stuff that makes sense. So for here, this is the GPU offloaded region because it's inside target, but there's this like variable n is a scalar, and we don't explicitly mention how we want to transfer that to the GPU. So scalars by default are first private, meaning that every thread has a private version of this, the scalar, so n. And then also if a variable is declared inside of a target region, so here the loop variables I and j, then those are also private per thread. And just the last thing, OpenMP offload, like the previous parts of this, was talking about expressing parallelism for code you write yourself. But a lot of the time you want to use a vendor library. So you can still do this with OpenMP offload, just with usually a couple of a couple of extra constructs. So GPU libraries, in particular, I'm thinking about math libraries here. You can use them for OpenMP offload. Usually the way you do it is specific to the vendor. So there's a slightly different way to do it with NVIDIA versus Intel, for instance. So with the example shown here is for NVIDIA. So you want to do a cuBLAS call, so cuBLAS dgem. So the parts in blue are like the cuBLAS parts. So I'll create a cuBLAS handle. And then with OpenMP offload, you would want to allocate memory on the device. So you can do that as you normally would with OpenMP. So here, this is using OMP target enter data for 3 arrays, A, B, and C. And then the main thing about cuBLAS is that it takes in device pointers. And so we need to tell the code to send to cuBLAS the corresponding device pointer to these arrays, not the CPU one. So there's a special clause, OMP target data use device pointer, which says inside these curly brackets, use the device pointer version. And then you can call cuBLAS like normal, or like you would with pure CUDA code, and then cuBLAS device synchronize and destroy. So we can talk more about this at the hands-on, but this is just, I wanted to give a clear example that with OpenMP offload, you can still take advantage of vendor math libraries and other GPU libraries. And this is just a quick overview of the OpenMP offload modules on Polaris. This link here has all of this in more detail, and this will be covered in the hands-on later. But just to give a quick idea, there are 4 different modules on Polaris that you can use that have OpenMP offload supported. The NVIDIA one, programming NVHPC, is the default, and then LVM and the NVIDIA compilers are recommended. And then just quick plug for the hands-on, that's later today, and Halo will be running that mostly. And that's all I have. Thank you.
Thanks, Colleen. We have time for one quick question.
If we're trying to call eventually MKL on Intel on the GPU using OpenMP, do we have to do something similar like the device pointer?
Yeah, it's so I don't know who's talking, but I could, if you give me your name, I can maybe find you on Slack and send you a link. It's easy to do from OpenMP offload with Intel. It's not the exact same as NVIDIA. They have their own way of doing it, but it's similar, where you just add like one extra pragma line, and then you can use a kind of a normal MKL call.
And that works in Fortran too?
Yes. Yeah, and same for NVIDIA. If you use, you can also call like cuBLOS from Fortran OpenMP offload code with the NVIDIA compiler and call cuBLOS. You need to use like the Fortran cuBLOS wrappers, but I have an example if you're interested of doing that.
Thanks, Colleen. Okay, so let's thank Colleen again.